Hello, today I'm going to talk to you about the chemical spongistatin. Spongistatin is a macrocyclic lactone extracted from a sponge species in the East Indian Ocean. Sponges have been of medical interest since around the 1950s when two nucleosides, spongiogordine and spongiothiamidine, were extracted from a Caribbean sponge species. These proved to have anti-cancer properties and also were used as an effective treatment for the herpes virus. The analysis, extraction and research of chemicals from the sea is known as marine natural products, and this is a very important practice for many reasons. Firstly, the sea holds a huge amount of biodiversity which has seen less rapid evolution than terrestrial forms, especially sessile ones like sponges. Being stationary for millions of years, these genera have refined internal biological chemistry to a remarkable extent, having to fight other bacteria, other organisms, other similar species, for example, as opposed to putting evolutionary points into escape mechanisms, defense, predation, for example. Marine product research is also super important environmentally. This is because the coral reefs hold about 80% of marine species for the whole ocean. However, corals are under huge threat from human expansion and human pollution. There are many undiscovered possible life-saving chemicals out there. However, we're destroying the coral reefs faster than we can research them. So any field or area that puts priority on this ecosystem is of great value and importance. Many chemicals since the 1950s have been extracted and used for medicinal research from sponges and their symbiotic bacteria. And since then, multiple anti-cancer related drugs have been created. Spongistatin in particular has showed strong toxicity to human tumour cells and inhibits mitosis in cancer cells greatly. Cancer is a huge killer and kills one in 6 people around the world, so any advancement in this area is really important. Hence its name, macro. Spongistatin is a huge molecule, and I'll only be covering a small amount of its synthesis. Thank you. This is our starting molecule with our 3 reactants. The fluoride ion attacks the silicon, and it can form a very strong bond with the silicon due to its high ionic properties. This causes the alkyne to leave. The alkyne is a better leaving group as it's more acidic and it can stabilize the negative charge. This makes it a better leaving group over the propyls. The imidazole then forms a complex with the triethyl silyl chloride, which makes the chloride leave, which allows the lone pair on the hydroxyl group to attack the silicon, which makes the imidazole leave. Then the negative charge from the alkyne takes the hydrogen from the hydroxyl group, which then forms our final protecting group. This is then attacked with a Grignard reagent to form our product A. This is our molecule for the second step with our 2 reagents. The methoxy base deprotonates the thioacetal to form a nucleophile, which can then attack the alkyne in the anti-Markovnikov less hindered side due to the fact that the ester can stabilize the negative charge on the alkene. Then the negative charge on the alkene is then able to deprotonate the other sulfur, forming another nucleophile, which then attacks the alkene through conjugative addition. This forms the thermodynamic product over the kinetic product because the methoxy group on the attached to the carbonyl reduces the reactivity, and therefore this more stable product is formed. This then deprotonates the methoxy to form a single carbon bond through conjugation. This is then reacted with lithium aluminium hydride to reduce the ester into a hydroxy group, where the lone pair on the hydroxy group can attack the imidazole silane protecting group to form a protecting group. And then this is reacted with THF and butyl lithium to remove the very acidic proton attached to the 2 sulfurs. This then creates a very nucleophilic carbon, which can then attack our new epoxide ring molecule to open it up and add it onto our original molecule, which is shown here. Then to our molecule, iodine and sodium bicarbonate are added, which react with one another to form an oxidizing agent known as sodium peroiodate. I've put the stoichiometric equation in of what I think it is. This then allows one of the sulfurs to become oxidized, which then allows it to become a much better leaving group, and thioacetyl rearrangement can occur, kicking out one of the sulfurs and forming a thioene, a double bond with the remaining sulfur. This then, due to its electrophilicity, can then be attacked by a hydroxyl group, which can then become deprotonated, kicking out the sulfur and forming a ketone. Then a acetyl protecting group is added so that the silyl leaving group can be kicked out with a fluoride, as we've seen before. This is then oxidized. The hydroxyl group is then oxidized into a ketone, this giving our final product for this stage. Then we react it with our product from the first stage to give our final product. Hi, and that was my part synthesis to Spongistatin. I hope you had fun. I know I did. See you next time.